Going to be a real quick video about the history of the periodic table and discuss a little bit about electron configuration and some of the rules of electron filling. So, as far as the history of the periodic table goes, just to back up a little bit, we can go back to history as far as the Greek philosophers. And back then, the Greek philosophers really believed that all elements were made of, or sorry, all substances were made of four elements: earth, air, fire, and water. And this remained for a really long time. There was a Greek philosopher named Democritus, and he believed that there were things such as atomos. We did discuss this last year, so I won't go into too much detail. But due to some politics early on, it took a very long time until anybody knew any different. So, somebody we didn't talk about in the late 1700s, Dobereiner, was the first chemist to actually recognize that there were patterns in some of the elements. Now, keep in mind there's a lot of things that happened between the Greeks and now, but that said, he was the first one that kind of recognized that there were these patterns. And he called them triads because he found them in threes: chlorine, bromine, iodine, and we know them all to be halides or out of the halogen group. But as he started grouping things together, he was only finding three things, and it was basically because he was finding some of the lighter elements, and so they didn't have that many elements to really compare with. But John Newlands, and we did discuss him last year, John Newlands was one of those that figured out there were enough elements that had been discovered at this point that he realized that there was a repeating pattern about every eighth element. Now, there were some hiccups along the way because they were ordering the elements by their mass, and we know that that's not how we arrange them now. But the other mistake Newlands also made was he compared it to this musical scale and the octaves, and because of that, the scientific community pretty much ignored a lot of his findings. So it wasn't until Meyer and Mendeleev started to work on a grid or a table that we now call the periodic table. Now, they were both working independently, and Meyer was actually the one that found that our elements had an independent positive charge to them. So, in other words, kind of figured out that protons were our identifying characteristic of all of our elements. But he and Mendeleev were both working at the same time, independently, and unfortunately, Mendeleev normally gets most of the credit for the periodic table. One, he published first, and second of all, he predicted the existence of unknown properties at that time. So he tends to get all the credit. So in 1872, Mendeleev published this first table, and the elements of gallium, scandium, and germanium were unknown at that time. And he predicted their existence. He actually put a blank part in his grid and said, the pattern doesn't line up here, kind of like what Newlands was saying, that the pattern wasn't exact. Well, it wasn't exact because we were missing a few elements and we weren't ordering them correctly. Now, that said, well, let me back up just a second. Here's a look at what his original table looked like. So you can see he had groups 1 through 8, and he was lining up based on properties, and they had just enough elements that they could kind of figure out what was going on. But you also notice he's missing a few things too, and this is really what gave him most of the credit. Now, Mendeleev's table was still based on mass, but once they reordered all of it, then we started to see some of the patterns that we know today. So the second part of this video, again, I just want to talk a little bit about the electron filling order and how that correlates with the periodic table. So the three rules that you know for orbital configuration or electron configuration is Aufbau principle. We always fill electrons in order of energy levels. But when I say that, please know that there's this exception that we always have to go closest to the nucleus moving out. But in general, the lower number energy levels are closer to the nucleus and the higher energy levels are farther out. Pauli exclusion says that we can only have 2 electrons in any orbital and they must be in opposite spins. And Hund's rule, the one I like to call electrons don't like roommates rule, is that they will spread out if there are more than one orbital, if there is more than one orbital in a sublevel. So we see this in things like the p sublevel where there's 3 orbitals. We'll see one electron go in the x-axis, the next one will go in the y-axis, and the next one will go in the z before they start to double up. And so that's a good example of Hund's rule. So valence electrons, definition-wise, these are always the electrons in the outermost principal quantum level of the atom. So they're always the ones that are given out in terms of ionic bonding or the ones that are shared in covalent bonding. And if we were to look at an electron configuration like I have written down here at the bottom, the 4s2 right there, because this is a 4 and this one is a 3, these are my valence electrons. So iron has 2 valence electrons in that 4th energy level. The other electrons are called the inner core electrons, or just core electrons. And so this 3d6 in this electron configuration represents core electrons. So the thing to remember, just because our electrons are filling in an order that have the lowest energy level first, or the ones closest to the atom first, that doesn't mean that the last one in is the first one out. So let me talk a little bit about that. So as we know, 4s2 fills before 3d6 because it's closer to the nucleus. However, if this were to lose electrons, I'm not going to lose it out of the 3d6. The last ones in are not the first ones out. The first ones out are going to be the valence electrons. Again, those are the ones that are involved in bonding. Those are the ones that are lost first. So if I were to make this a Fe2 plus ion, I would actually take away that 4s2 because those are the ones that would be lost first. All right. So as you know, the elements that are in the same group, these same patterns that we've been talking about, everything in the same group has the same valence electron configuration and therefore has the same chemical behavior. And this is an example of periodic law that we talked about back in, I believe it was Unit 2. So hopefully that concept now combining with the electron configuration information is starting to make some sense. There is one other thing that I want to talk about in electron configuration that we didn't really talk about last year or earlier. Transition metals can be a little weird when it comes to electron configurations and which ones they lose first. And copper and chromium in particular are exceptions to the general rules. Now, copper and chromium are right here on the periodic table. They're in the first D sublevel that we see here. And if you look, chromium is the 4th one in and copper is the 9th one in. So what we would expect chromium to do, and I'll kind of skip this part, the first 1s2 all the way up to 3p6, because that's expected. This would all be part of a noble gas configuration. But from here on out, I get 4s2, 3d4. Now, as you remember, d orbitals, in the d sublevel rather, there are 5 orbitals. And if you look, this leaves 1 orbital without an electron. And that's not as stable as chromium could get this. So what actually happens, and again, I'm going to kind of space this out here, is one of these electrons in the outer level here, one of my valence electrons, gets promoted up to the d sublevel. Now this is further out from the nucleus, so it kind of gets promoted up out into here to give the d sublevel 1 valence electron each, or one electron each in those orbitals, leaving the 4s1 all by itself, which of course it usually loses when it comes to ionic bonding. So the other one that is strange is copper, and it does something very similar. So again, I'll space these out. These are the last electrons that are added to copper. And again, I have my 2 valence electrons in the 4s2 orbital. And in my d sublevel, I only have 9 electrons when it maxes out at 10, which would give it a pseudo noble gas configuration. It would give that outside orbital a full configuration. So copper does a similar thing where it will promote one of these valence electrons into the d sublevel and make it a 3d10 right here and leave one valence electron left in the fourth energy level. So this is also why we normally see a copper 1 plus, even though copper is a transition metal and we would expect to see a 2 plus charge. Chromium is the same way. We would normally see a 2 plus charge out of a transition metal, but chromium tends to go to a 1 plus charge because it's left with just one valence electron. Now, technically speaking, these both have 2 valence electrons, but they do this kind of promotion of the electrons to get some stability. So as far as the orbital rules go, we said that Aufbau rule says that they all go in energy level order, but please keep in mind this is what we've talked about before, that the d sublevel is not going to fill with the energy level of that row. So it's always going to be one energy level lower. So the s orbital, that is one energy higher than the d, is going to fill first. So that 4sd will fill before, the 4s orbital will fill before the 3d will. And then the lanthanum and the actinide groups, lanthanide and actinide groups that are at the bottom of the periodic table, that are in the F group, are going to be 2 energy levels lower. So if we see here 6s2, 5d1, we actually end up with a 4f14 in there. Now there are some exceptions to some of the filling orders that happen here. And I'm going to just tell you right now, you are not expected to memorize these or know these outside of that the D group is 1 energy level lower and the F group is 2 energy levels lower. Outside of that, you are not expected to know any other exceptions. So outside of that, I believe that pretty much finishes this section. So I hope this is helpful, and as always, if you have any questions, please let me know. Thank you.